Question was just asked of me of why a chiropractor is doing oral cancer research. That wasn't quite the question, but I reformulated it. I was a chiropractor and one of the first chiropractic researchers. My first article was published in 1985 on N of 1 designs. But before that, I was an undergraduate in psychology, and I got a master's in applied behavioral science, which is research methodology and statistics and program evaluation. Went into chiropractic practice for 12 years in Northern California. I worked with Stanford spine surgeons and El Camino Hospital. I was really a part of the medical system up there, which I enjoyed very much and was able to help patients. And then in 1999, I sold my practice, worked for an internet startup that failed after a year in the bubble. I mean, we all went down together. And then I came down to the University of Arizona, got my PhD in research methodology and program evaluation. So it was in the School of Psychology. I'm not a psychologist, but I found that psychological research methods are pretty cool because humans are complicated, and a lot of the problems that healthcare is trying to solve are also complicated. So this is an example of taking a psychological research tool and applying it to biomarkers. Let's see if I get this to work. This is actually the paper I published on this, and you're all welcome to get a copy if you want to email me. Was phase one of a two-phase program that I created. This first phase is develop a method for identifying informative biomarkers. Now, this is an idea I had not run across before, which was some biomarkers are more informative than others. And we'll talk more about that. And then phase two is a method for testing biomarkers to best reveal the stage or pre-stage of cancerous tissue. And I'll just talk about where that's going to go, and I welcome any collaborators on this. And these methods are applicable to orthopedics and any other medical testing, blood testing that's going on. So the project genesis was that I was in Malaysia for 3 years, teaching in a medical school, very similar to this one. We had a dental school involved in the same campus, and we had nutrition and dietetics, medicine, and a couple other things that I'm not remembering. But this is a beautiful picture of the Cameron Highlands in Malaysia. And these are dentists in Malaysia, up in the Cameron Highlands. Malaysia is wonderful people, beautiful scenery, and the food is exquisite. It's kind of the Indian influence and the Chinese food. And so, however, they're catching on to the American Western diet now, and diabetes is really rampant. But and there's a McDonald's on every corner and so on and so forth. So Malaysian dentistry is technically quite sophisticated. The problem is that out in the jungle and remote villages and things, they might have this kind of equipment, but testing for oral cancer might be a problem. Now, oral cancer in Malaysia is, the three main reasons for it are the salted food diet, and this is actually salt on the food. I mean, that's a fresh food market that I went to one day. I took a picture of this. I don't know what that is, but this is some kind of vegetable, and they're catching on to tobacco, another gift from the Western world. But salt is a constant inflammatory substance. Nasopharyngeal cancer and oral cancer is perhaps caused, but is aggravated by that. And then this is the betel nut. Is that how you pronounce it? Betel? B-E-T-E-L? And this is kind of a source of pride in the Philippines, I guess, where the darker your teeth are, the more beautiful you are, the more authority you have in your tribe or in your community. It's hard for us to imagine that. I look at that. But it's quite a carcinogen also. So the screening might require a biopsy or just visual inspection and a pathology testing. When you're 100 miles from anywhere and the average temperature's about 95 degrees and the humidity's about 95 degrees, your samples won't last very long to be shipped, and you may not have refrigeration and things. So it's important that we be very efficient in a developing country, especially in finding ways to test for different kinds of cancer. Saliva is kind of a hot topic now for screening for cancer and diseases throughout the body. David Wong over at UCLA, I visited his lab. Ann Spillard calls him the Spit King, but affectionately. But the promise here is that you might even detect cancer at the pancreas, liver, breast through spit eventually. So it's a lot easier than taking blood. Most people don't mind it so much. And as you can imagine, when you get cancer, your metabolism gets crazy and you start producing different chemicals than you normally would. So proteins, RNA, lipids, etc., those things are circulating through the body and they'll show up in the mouth. And then with a spit, we might be able to detect those biomarkers that are associated with cancer. Oral cancer is the most proximate kind of cancer, and we'll start with that. So, but our mouths are filthy, and so there's so much noise in there. To identify the biomarkers can be tricky. And some biomarkers go up a little bit with cancer, some go down a little bit with cancer, and some go off the charts. And what that translates to is some biomarkers are good for identifying cancer, others just add a little bit of information. So we talked about the preservation issue. Again, you can't ship stuff. Well, the climate there is very damaging to samples. So how may psychological science help? I kind of made a plug for that earlier. They have developed, I don't think psychology is going to be around in 50 years, frankly, because of evolutionary science, but there's considerable complexity in humans, and so over the last 50, 60, 100 years even, we've developed good methodology for measurement and for analysis. And it's psychology's bread and butter to measure things inside us. IQ, ability. You give you a test, and if you can answer the questions, we'll say you are living up to what we're trying to measure. If you're a smart person, we'll ask the difference between a koan and a koran, and you will know that. I mixed it up in an IQ test. It's kind of a sore point with me. But anyway, we have an illustration here of measurement of IQ. We'll ask 100 questions, and each one of those will kind of give us a reading of what the intelligence quotient is for a person. Dexterity, I think it's undermeasured for medical education, frankly, and dental education, because manual dexterity is a big part of being a professional in those two areas. And so these might not be questioned so much as demonstrations of some kind where you're graded. And the same thing, again, this is the analogous process for detecting cancer. We have thousands of biomarkers that might tell us whether someone has or doesn't have cancer. But not all biomarkers are created equal. Some are informative, some are just meh, and we'll show you some of those. So here's a biomarker assay test for different kinds of cancer, melanoma, leukemia, colon, and there's a number of biomarkers that are organized by cluster as to where they're informative. This is still, now I'm not an expert in this at all. This is a whole profession unto itself, but I wondered if we could simplify this by using a few biomarkers, kind of the same thesis I've been talking about. We could identify the most informative ones, or is there an order of maximum information value, reduce the need for preservation, and make cancer screening more affordable. As you can imagine, some of these, like I was just showing you there, some of these assays can be very involved, expensive, and difficult to do. Certainly can't do them in the field. So the phase 1, sensitivity, specificity, and positive predictive value are what we're most interested in. Everyone know what sensitivity is and the difference between sensitivity and specificity? Okay. Sensitivity, this is the state of having a disease here, and this is the state of being disease-free, and a positive test result and a negative test result. So here's a correct decision, a correct finding. The test matches the disease state. This represents sensitivity. That is to say, of all the people who have the disease, the people who truly have it, that's called sensitivity. And this is specificity, which is of all the people who don't have the disease, this correctly identifies them. There's false positive and false negative. Bear with me. Anyone bored yet? Okay. Yeah, this is the stuff I had to swim in for a couple of years to get it on this project. Now, on a more fun note, I think how many remember Pac-Man? See, I was afraid somebody in the back wouldn't. I mentioned to my postdoc today, we have a postdoc now, the slide rule. And she said, I'd never heard of a slide rule. So. You heard about him. All right. The gray beard is just, well, you've been dyeing it gray. So if we use the Pac-Man analogy, and I put this on a poster, presented it, and people didn't appreciate it as much as I did, that the general and sensitive biomarkers to an anomaly are sort of over here. This is a big screener. It might be some indication of general inflammation in the body. I can't pronounce the words right now, but ESR, for example. That might be your first screen. And if you have some inflammation, this will kick it out to here, but dropping out, and I'll have another picture on this, dropping out will be the people who don't have inflammation. If they don't have inflammation, they don't have cancer, for the most part. I know there are exceptions. But if they do have inflammation, let's move them to another biomarker. So the positive tests from inflammation move to another biomarker, which tests them for some other indication, general indication for cancer, and it becomes more and more specific. The tool for this is called the likelihood ratio. And it's like Wagner, not as bad as it sounds. Somebody told me that once. Anyway, so likelihood ratio is sensitivity over 1 minus specificity. In English, that means true positives over false positives. So I found it's a very powerful tool for sorting biomarkers. Sort of the Pac-Man in reverse thing. This is part of a poster. Each biomarker is conditional upon another in the way you have to think about this. We've got the prevalence of a disease is 1%. HIV in the United States the prevalence is 1%. Does that strike anyone as high or low? Seems high to me, but scary high, but it is. And so our first biomarker separates out, cuts it down to this much, 1,530 cases that came out with a positive test. And you can see the prevalence within this second biomarker is 15%. So we've gone from a prevalence of 1% to 15%. Biomarker 2 cleans it up again. Prevalence within the smaller sample is 73% in the 244. And then finally, I get a sample after 3 biomarkers of 97% prevalence within this sub-sample. And that's only 80 left. Are there false negatives? Yeah, there's a few. And you as clinicians and researchers will want to say, am I more willing to have false negatives or false positives? There's the art to this, and we would have to talk about that. But get the idea? So we're concentrating the disease state. When you plot the false positive or 1 minus specificity with the sensitivity, you get this area under the curve chart. And what this means is everything up in this area is the most accurate test you can have, and everything below the curve is not really adding any information. So each one of these represents a biomarker. This that I was looking at. This is live data from my analysis and from my paper. And what we can do is we can reduce the number of biomarkers and have it squeeze up into this corner by only selecting a few really good biomarkers instead of this kind of scattershot idea. All right? I used to call it a shotgun, but turns out that means something else. So I promised Mark I wouldn't get mathematical on you, and I did divide something there. But anyway, these are biomarkers gathered from meta-analytic literature and then plotted. Sorry. So some of these biomarkers are really good with specificity, like this one. And some are good with sensitivity, like that. And then there's all the stuff in between. This is a very consistent biomarker, but it's not very accurate because it needs to be up at the corner. And then this is just neither accurate, well, it might be somewhat accurate, but these circles, these large lines here mean error. Those are that's how much error you might get if you took that point, HOXA9, for that biomarker. You would find out there's a lot of inaccuracy in that measurement. So down here, these last 2 panels are examples of taking sensitivity over 75%, specificity over 75%, and getting an AUC of 0.92. 1 is perfect. Nobody gets that. 0.9 is really good. 0.8 is good. This is 0.92, theoretically. And then if I just throw everything, sensitivity 0.75 or specificity 0.75, respectable, I get an accuracy of 0.8. Too many numbers? Are you with me? Questions? So what we're doing here is we're cherry picking the best biomarkers and using those. So the bottom line of all this is that these dotted lines here represent the number of biomarkers needed to be confident that somebody has cancer. And if we look at where 1.00 is the clinical, nearly clinical certainty. It's a positive predictive value, it's called. And if you have a disease prevalence of 2%, then it would take about 5 biomarkers to arrive at a clinical confidence that somebody has cancer. Of course, they'd be referred out to a surgeon or an oncologist for further testing. If you start with the lowest likelihood ratio and work backwards to the highest, it takes 15 biomarkers to reach almost certainty that a person has cancer. So going down this way is lower and lower prevalence of disease. So we get down here with 0.0002%, vanishingly small type of thing, but it could be a rare disease. And when we do that by ordering from most to least likelihood ratio, you get 10 biomarkers, top 10 biomarkers. If you go with the least to the most informative, you need about 20. But in neither case do you need 1,600, unless you want to, if you're worried about some kind of reliability of your test. So conceivably, and I'll tell you more in a minute about this, but this could really trim down the number of biomarkers you need. This is another demonstration of isolating the informative. And then this is the Pac-Man. And so the summary is, optimizing biomarker information improves accuracy with fewer biomarkers. And this could be applied for any medical test. We should always think of medical tests as kind of nested within each other. If I get a positive on this test, did I get one here? And then you really have increased your accuracy. If you do a series of tests and just say, well, gee, those are, half of them are indicating something, I'll do more tests. It's not that efficient. And I think what osteopaths can do and what dentists who are public health oriented could do is be more efficient with the testing and reduce hospitalizations. So preview of phase 2 is that the biomarkers will work like this. Cancer over here. This is a test we did on drug-drug interactions. We compared nurses, doctors, students, medical students, and pharmacy students. The easiest information to get is at the bottom. Nitroglycerin and Viagra don't mix. And almost everyone got that right. Why? It's on TV every night. Even if you don't want to know that, As I say, I'm glad my grandma's dead. She would just be mortified. And so the most difficult are like warfarin and gemfibrozil, and so on up here. The point of this is the construct we're trying to measure over here, their knowledge about drug interactions. And we can get, from organizing these test questions, we can get a pretty good profile of their ability to know this. And the problem is, everybody gets this, then there's quite a gap here before the next one. If we could smooth this out, kind of equally distribute those as biomarkers, we could detect almost any phase of the test, of the cancer. If we find out that someone has cancer, precancerous tissue in this area, let's say, but they come up positive on a biomarker test that skips all this, we're going to think they don't have cancer. Now, the problem is with phase 2 of this is that we need a steady progression of the disease state in order to test this method. And I'm not sure how to do that yet. Because in most cases, cancer research is you have cancer or you don't. So there's not any progression that we could test the biomarkers against, as far as I know. So if anybody knows anything about that, let me know. So any questions, comments? Inder?
First of all, you have to, so first you have to understand the disease pathogenesis. That's what the biomarkers is. So right now, this is a shotgun approach, right? ESR, well, can we predict, an ESR change, sedimentation rate? I mean, before, again, I was born, people were using it. But the thing is that, so this is going hand in hand in understanding the disease pathogenesis. You're relying on dysplasia, right? You're looking for cheek samples and you're relying on dysplasia. You're looking now at a molecular level. This technology allows you to do all these things, but you don't know the disease pathogenesis yet. So this will probably lead you to understanding how does disease form at a molecular level, when they say genetic level. So that's why there is this disconnect, apparent disconnect. Some things are moving much faster than really understanding where the disease is happening, right? So
that's a good point. I would say what this could, the work that I've done here could do is direct future research. Here are the most promising biomarkers. Forget about these guys. Let's go down here. I mean, with a lot of replication, and when you're very confident that you're on the right track for good biomarkers. So, yeah.
I think that an analogy to dental would be looking at when some of us went through dental school, 70s, we were looking at quantity of plaque, and we thought that's what was related to periodontal disease. And then it became more aware that it wasn't the quantity, but it was the quality of the plaque. And so we started honing down from broad to narrower. Now we've got the whole oral microbiome, and we're finding out things that we had no clue about before. We were able to culture maybe 30 different bacteria. With the oral microbiome, we're looking at thousands. And so what are the interrelationships there that we never understood before? So I think it's just a matter of time before we get to all of that. But I mean, what you're saying, Amy, makes perfect sense. It's just a matter of honing it down to that level.
Yeah, so I was in Singapore last fall at a cancer conference. Most of it was way over my head. Really, really smart people talking really, really fast. And I had no grounding in it, so I didn't really know. But I did meet a new company. They did a presentation. They're called Sengenics. They have offices in London, Singapore, and Tempe. So they're coming. One of them is coming next week to talk to us about this. When they read my paper, they said, oh, you know what? That's what we're finding. We're finding 5 to 8 biomarkers consistently show problems, and everything else is kind of not adding that much information. So I want to invite you and hope you can come next Thursday for the presentation. We're going to potentially do some collaboration together. They're interested in my ideas, and they run thousands of biomarkers. And what they're saying is it isn't the presence of the biomarker, the chemical molecule, but the shape of it, which is isomer, is it? Or anyway, chirality. Anyway, so organic chemistry is 40 years old for me, or 50. Anyway, get the idea. So they're saying the shape is everything. If you've got BT540 as a biomarker, it may or may not be a problem because shape of that is the problem. Where does it end, Mark? Where do now we've got 30 types of bacteria and plaque. I mean, it's getting increasingly complicated. I hope we can catch up with it somehow. Okay.
Thank you.
Thank you.